What's up, you Bosnian basket-weaving brainiacs? Today we're going to be talking about motion with constant acceleration, aka the SUVAT equations, okay? Now this is going to be kind of like a review, okay? I'm going to go over things pretty fast if I can underline the title. Okay, we're going to start off very simple. We're going to think about this question. Let's say let's say you're in a car and the car is going 30 miles per hour, okay? How many miles are you going to go in that car in 1 hour?
No, listen, if you're going
30
miles per hour.
How many miles are you going to go in 1 hour?
I don't know. What?
Well, the hint is right there. We're going 30 miles per hour, so in 1 hour we're going to go 30 miles. So what about 2 hours? How many miles are we going to go in 2 hours?
So do I divide something?
No.
The answer is 60 miles. If you said 60 miles, good job. Well, we can generalize this a little bit, and we can say that the displacement is equal to the velocity. This is an example of a velocity, by the way. Actually, this is an example of a speed, but if we say like in a certain direction, then this is an example of a velocity. Okay, and times by time elapsed. I make the distinction here, time elapsed, because I'm sort of thinking, kind of want delta t, you know, kind of thing. But yeah, displacement equals velocity times time. Pretty straightforward. But one thing we need to be wary of is when we were asking this question, when we were doing this question, a hidden assumption that we had is that the car is always moving at 30 miles per hour every sort of like second of the journey. Every single second, you know, it's always at 30 miles per hour. In other words, velocity is constant. Okay, so then that begs the question, what if we were at 30 miles per hour, right? But then we went to 40 miles per hour and we made this change over the course of, let's say, well, a bit something reasonable. Let's say we made this change over the course of 5 minutes. In that 5 minutes, right, how far did the car go? That's the sort of thing that we're trying to deal with today. Oh, and this is assuming that we accelerated in a linear, you know, constant fashion from 30 miles per hour to 40 miles per hour. And I'll explain what this means with a graph, let's say. Yeah, with a graph. So we're going to draw a graph like this. So this is a very common way and useful way of representing motion, especially velocity. So we have velocity on one axis and we have time on the horizontal axis. This should be pretty familiar. You know, even if you haven't studied this does seem pretty intuitive, you know, to represent things in this way. And we're going to be dealing with sort of motion sort of like this. So we start at 30 mph here, and over here 40 miles per hour. So basically the time elapsed between this is 5 minutes. And when I say acceleration is constant, literally what I mean is that we got a straight line happening here. We're not doing anything crazy like, whoa, you know? We're not doing anything crazy like we went at 30 and then we went to like 1 billion over there and then we came back to 40 miles per hour over there. We're not doing anything crazy like this. No, we don't want craziness. We're just talking about the simple case where acceleration is constant, aka this is a straight line. Okay, so turns out that the displacement is actually the area underneath this graph, this area right here. And I'll try and motivate, you know, give some intuition about why that might be, simply by talking about this case and showing that it's kind of similar. If we were to show this on a graph, it might look something like this. So the situation where we're just traveling 30 miles per hour, no changes, you know, just traveling 30 miles per hour, constantly. So notice that this is parallel to the horizontal axis. Yeah, and of course this is time and this is velocity here. And this is always at 30 miles per hour. So let's say that this over here is 5 minutes. So this is 5 minutes. That's the 5 minute mark right there. This is 0 minute mark. 0 minutes elapsed mark. And so, you know, we wrote this. Displacement equals velocity times time. This is the velocity. Time elapsed is 5 over here. If we multiply it together, notice that we can interpret this geometrically as the area of this rectangle over here. That's what we're sort of calculating when we do 5 times 30 over here, right? So you know, you can see in this example also that it's the area under the graph. And similarly, you know, it just so happens that it works when we vary the velocity as well. And in fact, this actually works even in the case where we have crazy crazy changing velocity, if we consider the area under this, then we actually get the displacement in this specific amount of time. But we'll look at that later. At the moment, we're just focusing on the linear case. Right, so that's what we're talking about. Okay, so the goal is we want to get a formula out of this. So yeah, like I said, we're looking at a situation like this. In our example, this was 30 here, and over here was 40. You know, let's just, yeah. MPH, as it turns out, is not a very convenient unit to use. What we more often use is meters per second for velocity, right? And we usually use seconds for time, because that's sort of like convention, but as long as you're consistent with the units, it doesn't really matter anyway. But now, you know, just to be more normal, I'm going to use meters per second. So velocity, meters per second. And we have time in seconds, because that's sort of like the base unit kind of thing. You know, it's standard basically. And we've got down here, we've got 5 seconds. Okay, this is looking pretty crazy now that I've changed the units, but whatever, we'll roll with it. Okay, let's say in 5 seconds we went from 30 meters per second up to 40. Okay, yeah, whatever, these are random numbers that I chose anyway. So this is the kind of thing that we're looking at now. Okay, like I said up there, the area under this graph over here gives us the displacement. So if we wanted to work out the displacement, right, we could draw a graph like this to scale. And what I mean by to scale is like we literally get graphing paper, we mark off 30 over here, we mark off 40 over there, we mark off 5 there, and we literally graphically calculate the area under this curve. Okay, we can do that, but obviously that seems a bit dumb when we could use mathematical methods to work out the precise area. And I'm just going to make it a bit more general as well, so we can derive a formula. So whenever we have a situation like this, we can just plug and chug and we're all good. So we're going to call this the initial velocity, u. Remember, this was 30 before, that was our initial velocity. And then we go up to some, or down to some final velocity, and this all happens within some time t. Now, I was sort of alluding to what the nice method to work this out without using graph paper would be, and yes, we can just do this in a mathematical way by literally working out the area of this shape here. So we can sort of split this down, there's a triangle right there, and we've got a rectangle like this. You see that rectangle? And we've got a triangle up there. So we can break it up into these simple shapes. Actually, let me use, like, I don't know, a different color or something. Bum, 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 bum. There we go, I kind of color coded it a bit better. So the triangle is red and the rectangle is blue. Wait, what? Not blue, green. My God, crazy. Okay, so yeah, we can work out the area of this triangle. If I sort of just copy this over, we can see what it's supposed to be. So let me just properly write what I'm doing. So the area under this curve is equal to area of triangle, which I highlighted in red, plus, of course, the area of the rectangle, like that. So let's think about what the area of the triangle is first. So cool. So we literally have triangle like this. We sort of just copy what we had up there. You can see that this distance over here is literally v minus u. Yep, v minus u. Then we've got the t on the bottom, and now we can simply use our area of a triangle equation, right? So we have area of triangle is equal to half times the base, which is t, times the height, which is v minus u. Right, now let's think about the area of the rectangle. So I just copy that rectangle over here so you can see easier. It's a nice looking rectangle right there. So we got t on the bottom. So we got t on the bottom, t. And we simply have u on the side. Actually, let's put it this side so you can see more clearly. Yep, that definitely is u right there. And so this area of rectangle is equal to simply, well, it's just u times t. So if we put this all together from here, we got half v minus ut plus ut. Now, here is the crazy thing. Keep this in the back of your mind. This is not the final form we want to remember yet. I'm just going to have a quick detour and we're going to talk about acceleration. I've been mentioning this word acceleration this whole time. What do I mean by it? Well, of course, acceleration, what we're looking at is the rate of change of velocity, right? How velocity changes as we change time. So acceleration is dv. If we give velocity the symbol v, right, dv by dt, that's what acceleration is. So yeah, But that is in a very general sense. Acceleration is equal to dv over dt. In our case, if we're just looking at sort of like the discrete case, dv, we can think about delta v over delta t. This is assuming the acceleration is constant. So assuming a is constant, we can kind of do this. And delta v is literally, if we put it in terms of this v and u business up here, delta v is literally the final velocity minus the initial velocity. That's how much the velocity changes over delta t. Well, we call delta t the time elapsed, just t. So actually, we just want t here. And from this, we get a is equal to v minus u over t. So this is actually our first SUVAT formula. It's bog standard, very simple, very intuitive. The only thing is that you might want to rearrange it in a form where we isolate v, because you often want to find the final velocity of something, given its initial velocity and some other stuff like that. So we can isolate v on one side. So if we multiply if we multiply t to both sides, then we get the following. And if we add u to both sides, we get this. And so we get v equals u plus at. And this is the form that's better to memorize, because it's got v already isolated. It's good. So it could save you some crucial seconds when doing calculations or something. But really, you don't even really need to memorize it, because it's quite intuitive. So actually, when I'm actually remembering it in an intuitive way, I try to remember it this way. But this way is good to memorize. A little bit of a speed up, but hey, rearranging this to here, it's not that hard anyway. But hey, the reason why I bring this up now is because notice this v minus u thing over here. Wait, hold on a second, we had some v minus u business over here as well. And so what we can do is we can sub this. We can sub this v minus u. V minus u is equal to at. We can sub it into this v minus u over here. So essentially we get half at, that's what it was, plus ut. And of course we can just simply write this as half at squared plus ut. And you'll often find, so remember what the area of the curve was, why we did this in the first place. This is the displacement. And displacement is often given the variable symbol s. And so this is commonly written, implies s is equal to ut plus half at squared. Let's just cordon off all of this. Not too elegant, but hey. And the great thing about this equation is if we've got the initial velocity and we've got acceleration and we've got time, we can easily work out the displacement. But what if we have the final velocity? Well, we can do some we can do some substitution again. Remember over there we were using v minus u is equal to at. Okay, now what if we had the final velocity and the acceleration at the time, and we want to work out the displacement? Well, we can do some rearranging again, and we're going to use this fact again. So using v minus u is equal to at, well, we actually can work out the final velocity in terms of the initial velocity. So v minus at is equal to u. So put that to that side, put that to that side. Yep, v minus at is definitely equal to u, and we can just sub it in. So s is equal to, well, v minus at t plus half at squared. If we sort of expand this out, vt minus at squared plus half at squared equals vt. Yeah, we can actually take this at common, so let's say plus at squared, then we have minus 1 plus half. What is that? Why, it's minus half, of course. So we basically have vt minus half at squared. So there we go. S is equal to vt minus half at squared. So there we go. We got two different forms, and they're quite easy to remember because it's literally s equals ut plus half at squared, and then the other one is s equals vt minus half at squared. So there we go. We got our first three SUVAT equations. Very nice. Next one along. Simple thing, we're going to be doing the same thing actually. We're going to be considering the area under that particular curve again to try and get the displacement, okay? But this time we're going to go about it in a different way, but also quite simple. In fact, this might have been some people's first thought when they're thinking about how to find the area under this particular curve. Well, I say curve, but it's more like just a line, isn't it? What we can do is we can simply just consider this as a shape itself. and this shape is called a trapezium. So this sort of shape is a trapezium, this quadrilateral. It's got 4 sides, right? 4 sides, it's called a trapezium. These are parallel, and the other 2 sides are not necessarily parallel. They come in all sorts of shapes and sizes, these trapeziums. You might be more familiar with ones which look like this. There you go, that's a trapezium. The key thing is that these are parallel and these are not parallel. Whoa, very bad. And of course, if we sort of like bring this in, not looking at any of this, of course we have a trapezium kind of like that one. And of course these are not parallel, so yes, that is a trapezium. And there is actually a formula for the area of a trapezium. If you've been doing the trapezium rule in A-level maths, you know, should know this pretty well, but yeah. The trapezium, the formula is literally, so if we have A and B here, and we have some height, A, B here, and we have some height, as you can see it's been rotated over there, rotation, it's my little rotation symbol. The area of a trapezium is simply half A plus B times height. Okay, cool. So we can use that over here. So as you can see, this distance over here is just V. This distance over here is just U, and we got T along the bottom. So we can use the area of a trapezium to work this out. It's simply half U plus V times T, which is kind of a height over there. And remember what area means. It is the displacement. I'm probably hammering it into you guys at this point, but yeah, displacement. Oops. Displacement, of course, has the symbol S is equal to half U plus VT. There we have it. That one's quite easy, I'd say. Our 4th SUVAT formula. It tends to be the case that this formula isn't used as much, you know, because you don't really have questions that often where you are given the initial velocity and final velocity and the time, and you have to work out the distance. You know, that, you know, obviously it can happen, so it's worth memorizing this formula. I mean, you don't even need to memorize it because you can just think back to how we derived it. You can quite quickly derive this on the spot as well if you just draw a little diagram like this, but yeah. You know, as you use this formula more often, you'll sort of memorize it automatically anyway, so yeah. Now, from these different formulas, you might be noticing something. We don't really have any formula where, like, all of these formulas involve a t in them. Okay, so out of SUVAT, let's say we were given acceleration, initial velocity, displacement, and we want to work out the final velocity, and we're not given t. Then we should have a formula for this case as well. And that's what our next case is gonna be. Let's just write down what we want. So we want an equation with no t. So what we can do is simply try and isolate one of the t's, and from the equations that we already have, isolating the t here, not very good, because if we try and isolate this, we're probably gonna have to end up with some sort of square root in there, which is not that great. This one, again, square root. This one, yikes, why? When we can just use this simple one, so we can have an equation in terms of t. So using v is equal to u plus at, we can go ahead and isolate t. So v minus u over a is equal to t. Now let's say we sub this into this one, so we can try and remove that t there. And we get s is equal to half u plus v, t, which is v minus u over a, multiply a by both sides, right? So we get as is equal to half u plus v minus u. Now notice that this is perfect square, so we can do as is equal to half v squared minus u squared by completing the square. And now let's isolate for v, so we get 2as multiplying 2 to both sides is equal to v squared minus u squared, and if we plus u squared to both sides, we get v squared is equal to u squared plus 2as. And this is our final SUVAT formula. So, in summary, if we just want to write out all the different SUVAT formulas we know now. So, we got the easy one, v equals u plus at. Then, we've got s equals ut plus half at squared. S is equal to vt, minus half at squared. We've got this odd one out here. V squared is equal to u squared plus 2as. And we've got the other area one. S is equal to half u plus vt. And now we can use some magic. Boom. Okay, we fixed the handwriting a bit. But there we go. There are our 5 SUVAT equations. Actually, do it. Ba 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 ba. And I was like, boo 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 boo. Yikes, yikes, yikes. This line is not very good, is it? Oh no. 3D, woo, yeah boy. Ha ha ha. Hilarious.
85-gram pack of kecks.